save some time. So I think do we still have some time? Or should I start? Okay. Okay, so it's time to start. So I think it was a good midterm. Average was 82%. So, and there were 4 or 5 maximum points, like 25. And yeah, so it was genuinely good. Well done. Hopefully you will do the same on the final. Whoever will survive till final. Okay. Keep it up. All right, so today we will be talking about harmonic oscillator. Harmonic oscillator is another problem that can be exactly solved, right, analytically, although it's more difficult than particle in a box. And first I would like to start with reminding you where does the harmonic oscillator appear in quantum chemistry, right, in molecules. And I've already told you this once, but just want to remind you that whenever we consider full molecule with its molecular Hamiltonian, this time-independent Schrödinger equation, where we have both electrons and nuclear coordinates, this Hamiltonian contains kinetic energy of both nuclei and electrons, then potential terms that are Coulomb interaction between particles, and we can combine all these terms except the kinetic energy of nuclei into the electronic Hamiltonian, then solve the electronic problem first. That's what Born-Oppenheimer kind of suggests, that we do electronic problem first, and we will return to that problem. All right, so right now we will consider that it's already solved for us, and in the lab section you actually been solving this for several systems, starting with atoms. You will be considering the electronic Hamiltonian, and then Gaussian program that you are learning. That's the program that where you fix the nuclear configuration, it gives you energies and the wave functions and all sorts of properties that you may be interested in. Okay, and then once this is solved, Born-Oppenheimer approximation essentially consists in thinking that molecular function can be approximated as electronic function, where the nuclear variables kind of fixed their parameters when we were solving the electronic problem. It's electronic problem, right? Solved by Gaussian. And then in lab section, labs. And then the total wave function, that's what we're after in general, because this is only electronic part, will be a product of electronic and nuclear function, chi and phi. And in order to find chi, we talked about this, what we do, we project on the electronic function, we obtain the equation for chi in Born-Oppenheimer equation, approximation. That would be equation like this. And this is just another differential equation to solve. This is a function of nuclear coordinates. These functions are coming from the electronic problem, because electronic problem depends on what nuclear configuration you are considering. And these functions, they form the basis for kind of chemical thinking about the reactions, barriers, right? So when we consider A going to B, say A is a chemical compound in a certain nuclear configuration, B is its isomer, and in order to go from A to B, we need to go through transition state. That's kind of a general chemistry material, or kinetics, right? Then the energy that usually people use to do these plots, they are electronic energy. right? Not the total energies, because total energy is just one number. This guy is more interesting. It's a function, right? So it's how electronic energy depends on what nuclear configuration we're considering. This is pretty much the essence of the chemistry, because chemistry is about changing of the nuclear configuration, right, from point A to point B. That's, yeah, if A is hydrogen and oxygen, you bring them together. This is a coordinate where you bring them together in that very simple picture. And then B is water, originating from that. Although water would be probably more stable than hydrogen and oxygen. So you can think of this being hydrogen and oxygen, and this being water, because energy is lower, right? Okay, now this is very useful quantity also because it's needed in order to complete the problem, in order to solve for the nuclear wave function, and also to obtain the total energy, which is that one number. Okay, and so how do we do it? We usually have at this point this function, and there are certain approximations we can further do, or we can solve the whole problem, but in reality people usually do some approximations. I will tell in a moment why. So this electronic energy function can be written as a Taylor series expansion at the point of some minimum, right? So it could be this minimum or that minimum. You can use any of those. If you are interested in kind of nuclear vibrations or nuclear behavior around that certain minimum, then the electronic function can be presented as a Taylor series expansion. Since it's a minimum, then the first derivative of the function will be 0, because in the minimum we have first derivatives equal to 0. And so the first non-trivial term is the second derivative of energy with respect to the nuclear configuration, all right, taken at the point of the minimum, and there will be energy difference between r as a variable and r0 as the point of the minimum that we're considering, right? So plus higher order terms that we will neglect. Okay, so we will consider only harmonic, it's so-called harmonic approximation, where we leave the constant term plus the first non-trivial term, which is second order term. Okay, so instead of putting the total potential energy surface, we will approximate it using quadratic function. And for simplicity today, we will be considering the case where r is only one-dimensional variable. So generally it's multi-dimensional variable. It has directions, say, along the oxygen bond, hydrogen bond. All the atoms can move independently in the molecule. But for today's introduction of harmonic oscillator and its solution, we will consider the situation where our nuclear variable will be presented only by just one variable to make things simpler, because in a multivariable case, this is not really a constant, this second derivative, it's actually a matrix, right? So imagine you have x and y, you have second derivative with respect to x, second derivative with respect to y, derivative with respect to x and derivative with respect to y together, right? So it's a so-called, how do we call that matrix? Hessian, right? So have you heard that word? Hessian matrix. All right, so this is more complicated object. This is a vector, so this together gives you a number because it's two vectors, r minus r0 matrix Hessian, then another vector that must be considered more like a vector matrix vector multiplication, and it gives you at the end the number, which is a contribution to energy. Now, but today it will be only one-dimensional case. Now, as you can see from here, what we kind of will be dealing with in a one-dimensional case for this equation, Tn will be, say we have like one particle, one dimension, h bar squared divided by 2m, the momentum. Alright, so this is our one-dimensional kinetic energy, and our potential part will be then, this is a constant, we will call it k, right? And we will choose r0 to be 0. We can always choose the origin of our coordinate system in any point we want, right? So r0 will be chosen at 0, and we will be choosing our origin of the energetic scale, so that electronic energy at r0 is 0. So we will count energy from this point, so essentially from this point of electronic energy in a certain configuration. We will call that our 0 for the energy, right? Then in this setup, this term will simply be kx squared divided by 2. Okay? Because second derivative in one-dimensional case, it's not a matrix, it's just a one constant. We will denote that constant k. This difference will be x minus 0, so which is x squared. Right? So we have kx squared, and there is this coefficient 1/2 that comes from Taylor series expansion. Okay? So we got the problem because we have now Hamiltonian, which is called harmonic oscillator Hamiltonian. And so that Hamiltonian will be acting on the function chi of x, but because it's a chi and x, they're not really good together because, well, you can confuse chi with x. And so let me just switch to notation where I will be using, instead of chi of r, I'll be using psi of x. Okay? Since we're working with one-dimensional case, I'll just, instead of chi n of r, here, we'll use a different psi of x. And this will be equal E psi of x. Right? So this problem is a time-independent Schrödinger equation problem with kinetic energy like in one-dimensional particle in the box, potential energy as parabola, right? So that is called harmonic oscillator problem, because you can also think of it as some kind of support, spring with the hardness k and mass m. And so then, say this is our x coordinate, this is our 0. Then the Hamiltonian for this classical system will be exactly the same. If we quantize it, if we consider classical mechanics, then classical harmonic oscillator problem will be again p squared divided by 2m plus kx squared divided by 2. Okay, so it's kind of a classical analog of a molecular situation with 1 degree of freedom. Okay, and that's what we will be considering today, how to solve this equation. Okay. Now it turns out, I already said, it's going to be more difficult than particle in a box problem. And there are multiple ways to do that problem. Now, there is a so-called serious way of doing things. We won't do it. And the serious way of calculating solution of this differential equation would be presenting our function as some expansion up to infinity potentially, right? And once you have your wave function written as just essentially linear combination of x into the n, then you can put the function psi in the left-hand side of the equation, right-hand side of the equation, and figure out what should be relation between the coefficients Cn, say with Cn plus 2, Cn minus, because minus 1. Because once you differentiate, you will obtain series in one in left-hand side and series on the right-hand side. And of course, the coefficients of the same powers of x should be the same, right? But that's a long and relatively difficult way of doing, and then you need to guess what the function is if you know the relation between coefficients, right? So this is a relatively, exhausting way of doing things. We are not going to do that, but some textbooks go over that. So what we will be using is algebraic approach. We've introducing raising and lowering operators. So we will introduce new operators, and they will make the whole solution much simpler. Now before, that's what we're going to do today. Before we'll move on, this Hamiltonian can be made slightly kind of more tractable or somewhat can be reduced to even simpler form by absorbing mass into the coordinate. So let's say I introduce coordinate q instead of x, and the q is square root of m multiplied by x. So I introduce a new coordinate that is essentially it has a scaling factor, square root of mass multiplied by my old coordinate x. Okay, and so what does this give me? Well, first x is then become q divided by square root of mass, right? And if we have a momentum p of x, which is minus I h bar d over dx, right? Then we can say that essentially alternative momentum would be q momentum. It's minus I h bar d over dq. And there is, of course, relation between momentum for the x variable and for the q variable. We can either put, instead of, use the chain rule, right, d over dq, dq over dx in the derivative. Or here we can do the same, right? And we know what this is, right? Derivative of q with respect to x. Its derivative of q with respect to x will be square root of m, right? And derivative of x with respect to q will be 1 over square root of m. Okay? So that way we can say that essentially x can be substituted with q, but the derivative with respect to q, and that's the pq. So that means the px momentum is pq momentum multiplied by square root of m. Or we can also say that the pq momentum is px momentum divided by square root of m. Okay? So I'm doing all this to not to confuse you, but rather to, instead of dealing with the Hamiltonian, which was px squared divided by 2m plus kx squared divided by 2, right? I can write it down as pq squared divided by 2, because pq is px divided by square root of m. If I square pq, then I already get division by m plus k divided by m q square divided by 2. Okay, and so this can be written as pq squared. Actually, 1/2 can be taken outside, pq squared plus so-called omega squared q squared. That's the simple form of the Hamiltonian, where omega is like a classical frequency of oscillation. Turns out it's exactly the same. If you remember classical harmonic oscillator, then the frequency of oscillation is square root of k divided by m. If you have a rigid spring, then the frequency is higher, and if you have smaller mass rigid, the frequency is also higher. And in order to lower the frequency, you need to increase the mass. That's, by the way, we'll see later, because all this is related to IR spectroscopy and Raman spectroscopy. So if you want to characterize any organic compound, the frequency of the compound essentially that you can excite by radiating with IR or Raman, or essentially the IR range of the electromagnetic waves, right? Then you will get the IR or Raman spectra, and they are going to be characterizing the compound. Now, if you deuterate some of the hydrogens in the compound, then the masses will be increased, and the frequency of those vibrations, they will be decreased, right? And if the vibration contains only hydrogens, then the effect of the deuteration will be the highest. If the vibration contains not only hydrogens but other atoms, then overall change of the mass will be much smaller, and that's how in the experiment, by deuteration, people figure out what, say, particular peak in the IR spectra corresponds to. If it shifts when you deuterate, then it means it has a lot of the hydrogen character in it. Okay. Now, this is a frequency. This is now our Hamiltonian. Okay. And now it's time to introduce our lowering and raising operators, which will help us to solve the time-independent Schrödinger equation with this Hamiltonian. Now, for the future, I will refer to PQ as just P, okay, just to make notation simpler. And I'll be using atomic units, so H bar is 1. So that's my convention. Our Hamiltonian then is 1/2 P square plus omega square Q square, right? Very simple form. Okay. Okay, first I will introduce these new operators, and then I will explain to you why do we call them raising and lowering operators. So have a little bit of patience. So called raising, lowering operators. We'll call them B's. So the raising operator, B dagger, will be square root of omega divided by 2 Q minus IP divided by omega. And this is a raising operator. Lowering operator, which is also Hermite conjugation of raising operator, is omega divided by 2 Q plus IP divided by omega. Okay. So these are operators, and they may be slightly intimidating looking operators, but turns out you can actually write the Hamiltonian using these operators in the following form. B dagger B plus actually 1. Sorry, let me, probably the simplest way of writing this will be like this. Omega multiplied by B dagger B plus 1/2. Okay? So that's the form. So how do I obtain this form? It's actually quite simple. We start with the form right there, 1/2 p squared plus omega squared q squared, right? So then we need p squared and q squared. We can get them from defining p. How do we obtain p from b and b dagger? So what is P and Q? Can we kind of, if someone gives you B and B dagger, can you give me P and Q out of that, those expressions? Which one is the easiest? Q. How do you get Q? Say it louder, please. B dagger multiplied by B. Why do you multiply them? Yeah, but if I just want to obtain the Q, right? So then I can just add B dagger and B, and then the P part will be essentially removed, right? So Q is, and then there is a factor of 2, so what I end up, Q is, Q multiplied by 2 square root of 2 omega equals to B plus B dagger, right? Because if I add them up, then I will get Q multiplied by 2 square root of omega divided by 2, and that is square root of 2 omegas, okay? And P is just you need to subtract B minus B dagger, right? And then by doing a simple algebra, you can actually obtain that you need to subtract, divide by I, because P contains I there, and then multiply by omega divided by 2. That's the expression for P. Expression for Q then becomes very simple. B plus B dagger divided by square root of 2 omega, right? And if you take that and this, then you can obtain P squared by squaring them. And essentially, Hamiltonian then becomes, if you start from here, it will be omega divided by 4. For the P part, B minus B dagger. This is P squared divided by 2. That's what it will become, because P squared is a square of B minus B dagger, right? I squared will give us minus. Then we have square of this square root. This is omega divided by 2, and then another half, and that's 1/4. Right? So this is a P part, and then the Q part will be omega divided by 4 b plus b dagger squared. Okay. Again, it's very simple, because you square q, you get 1 over 2 omega, and then you also have another 1/2 and omega squared, so that boils down to this. And now it seems like this is complicated, but in reality, if you just do the square, then what we'll obtain is omega divided by 4 b dagger squared plus b squared plus b dagger plus b dagger b. And here, since we're working with operators, you need to remember that they don't commute, so b times b dagger is not equal to b dagger b. So when you square either b minus b dagger or b plus b dagger, you will get terms that are essentially, those terms will be different, b and b dagger and b dagger b. And then we'll have b dagger square minus b square plus b dagger b dagger. Okay. Now, in this expression we have massive cancellation except the cross terms, and then the cross terms allows us to formulate the Hamiltonian as, so we have two pairs, that's why we changed the quarter to half, and that's our Hamiltonian. Now there is one more step to get to this form, and that one step requires considering what is the commutator of b and b dagger. Okay? How can we calculate this commutator? Any idea? What commutators would contribute to the b dagger? Why don't they commute? Well, just look at the definition, right? So they have, what do b and b dagger have? They have position and momentum, right? So position and momentum, they don't commute. So, and they have them in a different way. So together, the non-commutativity of b and b dagger, it comes from the commutation relation between the position and momentum, right? So because position in b will commute with position in b dagger, momentum in b dagger will commute with momentum in b, right? But there will be kind of commutators between the q in b and p in b dagger, and p in b and q in b dagger. So I'll leave it as a home exercise, but the result is very simple. It's 1. Okay? It's very nice. So remember though, I'm working in atomic units, so that means h bar is 1. So in the same units, x and p, or we use q instead of x, q and p is I h bar, and so that means it's I. So what happened here is that when we substitute q and p to b and b dagger, then instead of having a commutator which is I, we have a commutator which is 1. It's still non-zero, but it's 1. And it's nice, because what does this mean? That means b times b dagger minus b dagger times b equals 1. Now, this means is that we can substitute b dagger always by b dagger b plus 1. right? As I promised, it's a pure algebra. You can actually code it in a computer, so the computer will derive all the expressions. Okay? So, because they are somewhat lengthy, but every step is actually very simple. It's just algebra. You just need to remember that some of the quantities do not commute, so you cannot interchange them, but you can multiply them and divide by constants. So, having this in mind actually allows us to treat this expression, right? And so we substitute b and b dagger by b dagger b, and we get omega divided by 2. B dagger b, now we have two of them, one here and one from this, plus 1, right? And if we divide everything by 2 inside the brackets, we will get the expression I promised you. Okay, so that's our Hamiltonian in raising and lowering operators. Now, I didn't tell you yet why do we call them raising and lowering, and why is this form so useful? Now I'll tell you. Let's say I will keep this. I'll erase this. Oh, it turns out that if, say, we have a wave function psi for our Hamiltonian, and it's an eigenfunction, so it gives us some lambda as eigenvalue, okay, then b dagger b also will be an operator for which this function will be maybe with some other eigenvalue, right? But it will also be this function will also be an eigenfunction of b dagger b. Okay. Why is that? Is it obvious? By silence, I judge that it's not obvious. So when two operators, this is an operator, right? And this is an operator. When two operators can share eigenfunctions, yeah. When they commute, right? So do they commute, h and b dagger b? Well, let's see. H is constant multiplied by b dagger b plus another constant, right? So this pretty much is omega b plus omega divided by 2, right? That's our operator, right? So you have this operator multiplied by constant plus another constant. Constant always commutes with the operator, right? Any operator, because it's a constant. So let's just see if we have, let's write the commutation of b dagger b with h. Then we have omega b plus omega divided by 2 b, right? So this is essentially sum of two commutators, omega b plus omega divided by 2 b, right? Now this is omega commutator of b dagger b. Any operator commutes with itself, right? So this is 0. then here, what do we have? Omega divided by 2 b dagger b minus b dagger b omega divided by 2. It's a constant. You either multiply function with a constant and then act with some operator, or you act with operator and then multiply by constant. Result will be the same. So this is also 0. You can think of b dagger b or b and b dagger because they have momentum in them. It's like a differentiation essentially. It couldn't be worse than that, right? And if you have a function that you need to differentiate, whether you multiply function by constant then differentiate, or you differentiate and then multiply function by constant, it will be all the same. Do you follow? Too easy? Should I go faster? You're falling asleep. Coffee is not helping. Maybe I should go faster. It's too boring. Anyway, so you can see they commute. That means if we can find eigenfunction of this, why do I bring this up? Because if we can find eigenfunction for b dagger b, then we're done. Right? Because that eigenfunction will also be eigenfunction of our Hamiltonian. We solve the problem. So this b dagger b is easier than this. It's just the constants and multiplication by constant, addition constant. So this is unnecessary complications. So this argument allows you to focus on the essence of the problem, which is you need to find an eigenfunction of b dagger b. Okay, so that's important point. Now we came to the another important point, which is why do we call them raising lowering operators? It turns out that if we take a function which is an eigenfunction of b dagger b, again, we use power of imagination. We didn't get that function yet, but we imagine we have it. All right? So imagine you have it. Turns out that it can be proven that if you apply b dagger on that function, this function also will be an eigenfunction of b dagger b. Okay? And this is remarkable, right? So you apply operator on a function, and it still stays a function, eigenfunction of this guy. Although this guy and this guy, they don't commute, right? So, but it's an interesting case, and you will understand why we are calling these operators raising operators, because they raise eigenvalues of the function, but everything in its own turn. All right, so let's just consider this. What is this? If we know that this guy is an eigenfunction of b dagger b. So we know this, and we want to know what is happening if we consider this. Okay, so let's just write it down slightly differently. We have b dagger, and then we will consider the following. b dagger psi lambda. Okay? I just moved the brackets. Right? I didn't do anything. I just moved the brackets. Okay? But we know that b dagger can be written as b dagger b plus 1. Right? So we can substitute this guy by b dagger b plus 1 psi lambda. Right? So then we open the brackets. We have b dagger, and then we have b dagger, or rather we kind of put the psi lambda inside. Right? Also, we know that psi lambda is an eigenfunction of B dagger B. That was our starting point. So this will help, because when we can substitute to eigenvalue, right? And then we can say, okay, psi lambda can be taken outside of the bracket again, and we have tau lambda plus 1 psi lambda. This is a constant, so it always commutes with B dagger, so we can change their position. Now let's summarize. We acted with this B dagger B on B dagger psi lambda. What did we get? We got a constant, and we got back our function B dagger psi lambda. So that this whole thing proves that this function is also eigenfunction of B dagger B. And if the original function was with eigenvalue theta, then the function that we obtain when we act with B dagger on the original function actually will be eigenfunction with theta lambda plus 1. So what B dagger essentially does, it increases eigenvalue of original function by 1. You can do the same algebra, and I will leave it as a homework exercise. All this can be repeated if instead of starting with B dagger psi lambda, you start with expression B dagger B acting on B psi lambda. Okay? So it turns out you can show that this guy will be, through the same kind of technique, it will be theta lambda minus 1 B psi lambda. Okay? You can see that it's also eigenfunction, but with eigenvalue that is by 1 unit lower than original one. Okay? That's why B is called lowering operator, and B dagger is called raising operator. Turns out that there is another problem we will study in this course about angular momentum and spin. So there we also will end up with the Hamiltonians that can be written as a product of lowering and raising operators. Turns out that whenever your Hamiltonian is written as a quadratic form, so that means you have, say, 2 raising operators multiplied, 2 lowering operators multiplied, plus lowering and raising operators, then all these Hamiltonians can be solved exactly. That's a special class. Harmonic oscillator falls into the special class of problems where we can solve them exactly. But we are just halfway through. Okay? Now, the next thing will be, now we know, even though it's a little bit maybe seem too imaginative at this point, but now we know if we have an eigenfunction of B dagger B, then that eigenfunction will be a solution of our problem. And also, if we act with B dagger and B, we will still get to the different eigenfunctions, which will also be an eigenfunctions of our problem, just with different eigenvalues, right? So we now know if we have one seed function, we can move up and down in the eigenvalue kind of hierarchy, right? So our ladder. We have kind of another name for this B dagger and B is ladder operators. They can actually, if you give them eigenfunction, they can produce other eigenfunctions with just different eigenvalues, right? So we just need one, and we're done. If we can find only one eigenfunction, we can find all others by acting with B and B dagger. Okay, that's the power of B and B dagger operators, because they allow you to move between eigenfunctions. Okay, of course it's still a little bit more complicated than if you remember particle in a box. We get the form of the eigenfunction where there was n. You change n, and you get a different eigenfunction. That's hard to top that, right? But with the more difficult problems, you are happy that, well, that you don't need to go after each eigenfunction separately, right? You can obtain only one and then produce others by acting with B and B dagger. That's the power of those operators. Now, how do we find that one? It's like they are criminal organization. You need to crack only one, and you will crack the whole criminal organization. Okay, that's the kind of idea here. We need to crack at least like a weakest point. We find the weakest point in this, and we'll be done with the problem. Now, the weakest point here is that the following consideration. If we look at this matrix element, what this is essentially it's an integral over, well, we have a q coordinate, right? So we integrate over q, and essentially we have this and this. Its absolute value of b psi lambda square. Why is that? Because B dagger is a Hermite conjugate of B. So that means the action of B dagger on this side is the same as action of B on that side. Okay, so that's the idea, because it has B and B dagger, they have I, and I, you can see that if you just do B star, that will be essentially B dagger, right? Because if you do B star, you need to change the sign in front of I, and that's what gives you B dagger. Therefore, pretty much B dagger acting on this is the same as B with a star. And this allows you to say that this matrix element is nothing but essentially integral over the absolute square of some function. Now, what does this tell us? Absolute value of some function, any function you give me, if I take absolute value and take an integral, this integral will always be more or equal than 0. It cannot be negative. Integral is the area under the curve. And if curve is always above 0, and the absolute value squared is always above 0, then the area under the curve will always be positive, or 0 in the worst case, right? So, this is all kind of straightforward. What does this tell us? Is that this will always be higher or equal, non-negative essentially, right? So no matter what function we take, if you act on B, well, sorry, if you act with lowering operator, you cannot go below 0. Okay? Okay, so what kind of conclusion can we make out of this? You can just take any function and keep applying the B, right? So what will you end up with? You cannot go below 0. So, but if you have 0 as a result, acting next time with B will also produce 0, because 0 multiplied by B, if you have 0 and you're acting with all this on 0, they will still get 0. So there is a, essentially what the bottom line here is that there is a bottom of this whole hierarchy of wave functions, and that's our weakest link in this series of eigenfunctions. Essentially, there is a function, I call it psi 0, where if I act with B on that function, you cannot go lower, it produces 0. And this is a big important point, because this kind of gives us actually the equation to solve. B is an operator. Psi 0 is unknown function, which is the easiest to find. And we know the right-hand side is 0, so we just write down the equation. B is the square root of omega. It doesn't matter really because we have a right-hand side 0, so we can easily remove that. QIP divided by omega, acting on psi 0 function of Q, gives you 0. Let's just see what P is minus I d over dq, right? So that means IP divided by omega is equal to d over dq 1 over omega, right? And so then our differential equations that anyone hopefully in this room can solve is the following. Okay. So can you solve this equation? It's actually a first order differential equation. You have derivative of the function multiplied by some constant equal to the same function multiplied by a coordinate with minus sign. If we put essentially everything on the one side, well, like derivative on one side and then function on another side. So what equation do we have? It's actually not more difficult than the equation you solved in the kinetics course, or B20, right? So thermodynamics, kinetics. So let's see. You have derivative of function with respect to Q. Then it's equal to minus omega Q function, right? So that's the, you can just separate variables. D psi divided by psi equal to minus omega Q dq, integrate, right? So this gives you logarithm of psi equals to minus omega Q squared divided by 2 plus C, right? And then this is all clear, right? It's just the simplest possible differential equation. That's the first type of equations they teach how to solve. It's like a first order, or it's like a kind of a what? It would be kind of a second order differential equation. Yeah, something like that. Not second order, but it's kind of related to kinetics. All right, so what does this mean? That means that our function CQ is some normalization constant, which is exponent of C essentially, then exponent of minus omega Q squared divided by 2, right? If you exponentiate this, then you have some n, which is kind of, we find n from the normalization condition, right? Because our function must be normalized. So n square integral of exponent minus q dq. It's a square of the function. This thing must be 1 because, well, we've done very well on the midterm, right? So everyone got this. It must be 1, right? And that's essentially this function. Now, and n square or n directly is 1 divided by the integral of So who knows how to take this integral? Integral of the Gaussian function. Okay, so it's a kind of a table integral. There is a way to do it using complex variables, but in order to make long story short, actually this is called Gauss integral, and you can just check up on Wikipedia. There is also, I don't want to stop on that. There is also kind of they explain how do you take it. And in this case, it's the fourth power of omega divided by pi. All right, so that's your n. Normalization, and the function is given here. Now, what is left is essentially to produce other functions, and all these other functions will be, if we take, say, b dagger and apply on psi 0, then you will get psi 1 with some constant, right? Because not necessarily when you apply the raising operator, you get exactly normalized function of your Hamiltonian. It may contain some constant. And so now we find what this constant is from the fact that what's our consideration here is that okay, our b dagger b, if it acts on the 0 function, it gives us 0. And then that means the Hamiltonian that acts on the 0 function will be omega, essentially b dagger b plus 1/2, acting on the psi 0. And that means the eigenvalue of the 0 function for the Hamiltonian is just omega divided by 2, right? Because b dagger b acting on the psi 0 is 0, because b acting on psi 0 will be 0, right? So that's the case. Now, if we have psi 1, then by definition what psi 1 is that b dagger b acting on psi 1, it's essentially 1 multiplied by psi 1, right? Because psi 1, we know it should be a function that is raised by the raising operator from psi 0, and psi 0 eigenvalue is 0. So for psi 1, eigenvalue when we act with b dagger b should be 1. Okay? And then h psi 1 eigenfunction will be omega divided by 2, omega 1 plus 1/2. 1 comes from b dagger b, 1/2 because it's part of Hamiltonian. So it's omega divided by half multiplied by 3. Okay? Now, returning to the definition of this constant, we can say that whatever function psi n we have, if we have function psi n, that means b dagger b equal n psi n, right? And then if we consider psi n inside the integral with b dagger b psi n, this part will be n psi n. N is a constant. That means n psi n psi n. So functions are normalized. That's why the integral of their eigenfunctions are independent of n will be always 1. So this matrix element is n essentially. Okay? Now if we apply b onto psi n and b dagger on psi n, they both will act like lowering operators. And so what they will do, they will produce the constant alpha and lowered values psi n minus 1 with that constant alpha, and this part is alpha star n minus 1. Right, something like this. This is a constant, alpha squared. So we can take it outside of the integral, and we know what this integral is. It's n, right? Therefore, alpha squared multiplied by psi n minus 1, psi n minus 1 gives you n. And what is this? Eigenfunction of any problem. If you normalize it, what's the integral? 1. I just told you that here. Independent of n, so here n is equal to n minus 1. So this is 1. And therefore, you have alpha square equals n. What's the solution of this equation? Square root of n, right? Is this the only solution? How many solutions does this equation have? 2. Who thinks 2? Who can give more? Come on, guys. Infinite number of solutions. Because alpha can be alpha real multiplied by any phase, right? And phase can be anything. It will all, well, like the phase factor will go away because you are considering only absolute square, right? So alpha r is square root of n, and then there is an arbitrary phase that can be any number. Phi can go from 0 to 2 pi, right? So any number you take, this type of number will be a solution. But we don't need any number. It's like a solution of Schrödinger equation always defined up to a phase. So we just make a particular choice where alpha is square root of n without any extra phase, because we don't really need that extra phase. Now what this all tells us is that it's just one extra thing, essentially. It's how raising and lowering operator, how do they act on our eigenfunctions, right? So if you have b and you have eigenfunction psi n, that means we have square root of n psi n minus 1. Okay? And the same kind of exercise can be done with the b star. B star acting on psi n, you have n plus 1 in the square root psi n plus 1. Right. So this is the action of individual raising and lowering operators on eigenfunctions, and also b dagger b acts on eigenfunctions producing their number, right? And the Hamiltonian, when it acts on psi n, it produces essentially omega n plus 1/2. Right? That's the famous harmonic oscillator eigens energies, which, as you can see, with n, they grow linearly. And if you take n and subtract n minus 1 energy, the difference, it always will be omega, because the dependence is linear. Now, we only know explicit form for ground state of harmonic oscillator. It's this Gaussian function, right? And you probably are dying to learn what are the other functions, right? And it's interesting because for harmonic oscillator, functions are not, well, they cannot be easily written as for particle in the box function. We can always write that psi n now of x is, or of q, is b's dagger into the nth power divided by n factorial square root acting on psi 0 q. Okay? So that's the general form. And by knowing what this is, knowing how to differentiate and multiply by variable, and taking the square root of factorial, then you can produce the functions. But explicit form is somewhat more difficult and not, well, involved, I would say, right? Because it has a name. So if you do that, n's factorial, then another expression one can write is omega q squared divided. This is a kind of a part that comes from the 0 order, and then the complication comes from these functions. They are Gauss, they are Hermite polynomials. I have named Hermite polynomials. Okay, and I'll just write down few first Hermite polynomials. 1 when n equals 0, 2q when n equals 1, 4q square minus 2 when n equals 2, so on and so forth. On Wikipedia you can find the rest. Also there are some, well, there is a general expression how to generate them, right? But unfortunately there's no easy compact form for these polynomials, because there are equations where you kind of, one of them is here, where you have some kind of a Gaussian function that you need to differentiate n times to get the Hermite polynomial. But essentially you need to differentiate n times to get to the nth order Hermite polynomial. And you cannot just write what will be the coefficient in the simple form. Okay? Now, this is all kind of complicated part. Now the easy part is, just let me visually present what we just achieved. And when it goes to solving time-independent Schrödinger equation, two things we always are interested in are eigenvalues and eigenfunctions. So the way they look is you have energy, right? The potential, say the coordinate system here, and this is the bottom of the parabola. The parabola is, say, kx squared divided by 2, right? And this is our 0 of energy. Now, the first ground state of harmonic oscillator, it's omega divided by 2, right? And omega is square root of k divided by m. Okay? So now, this is something that you probably heard about. When we go to quantum and we have 0 temperature, molecules do not stop vibrating, right? And this is about the so-called zero-point energy, right? So this is energy of the quantum harmonic oscillator at its ground state. And this whole picture of molecules not stopping vibrating, because classical understanding of what temperature is, it's constant motion of particles in the ensemble. That's what we study in thermodynamics, right? So that thing comes to freeze when you bring the temperature to 0, right? In classical picture, when we don't know, when we do not invoke any quantum kind of mechanics, then everything just freezes, position is clear, it's the bottom of that well, and nothing moves, right? But people thought initially like that's kind of the way things are. Then they realize, oh, that doesn't. If you assume that, you have some problems with experiment, low temperature experiments, right? And they needed to introduce that actually energy is still there, so you have this zero-point energy, and it's above the minimum. Now you may think that in classical language you may say that, okay, if you introduce quantum effects, molecules even at a zero temperature vibrate, right? Because in classical physics, in order to have some energy, something needs to move, right? Say, how does it have energy? It needs to move somewhere. But in quantum world, this is just an eigenstate, and if you consider probability density of the eigenstate, it's not time-dependent function. Essentially, it's static. In that sense, nothing moves in the quantum world if you are in eigenstate. Then you have other eigenstates. If you increase, say, this is n equals 0, n equals 1. The distance here, I'm a little bit off the scale. Let me be more careful. So this is omega divided by 2. Then I need to take twice of that distance. Say this is my omega, right? And this energy is omega multiplied by 3 divided by 2, right? 3/2 of omega. The distance is exactly omega. That's why if I want to probe system, I send the electromagnetic wave, and then molecule that has a frequency omega, it absorbs that energy, and I know from that absorbance that, okay, I have, say, water molecule that absorbs with certain omega, right? Versus, say, CO2, which absorbs at different frequency. And then all other levels, they are separated by the same distance, omega, right? And then this one is omega multiplied by 5/2, and so on and so forth up to infinity. Actually, you can pump as much energy as you want. This is going to be absorbing everything. Of course, this is not what happens in real molecules. That's why in real molecules the potential surface is something like this. And what works here very well at the minimum, considering things are harmonic, stop working higher in energies. And what you will study in the lab, for diatomics, for example, harmonic oscillator approximation works very well here. This is electronic energy. This is the distance between, say, two hydrogens in hydrogen molecule. But eventually, the potential surface is like this, so it's closer to so-called Morse potential, which you will study in the lab. But harmonic surface would keep going up, right? So it would be misleading to use harmonic oscillator approximation in the region where you have very high n's. What n is high? Well, depends on the molecule, right? But generally, we're talking about beyond 10 and higher, right? So then, just the real potential is different than harmonic approximation, because after all, we started introducing harmonic approximation by making a Taylor series expansion here at the minimum and cutting first two, like after the second term, right? In order to have a full curve, you of course would need the third, fourth, and so on terms of the Taylor series expansion, right? Those are called anharmonic terms. And those terms are actually this whole anharmonicity and this curvature of the potential energy surface. That's the reason why things break. If you think about it, if harmonic approximation would be valid everywhere, there is no way to break things, because essentially, no matter how far you stretch, they would come back, right? Because the stretching of anything would correspond to elongation of the bonds, right? Energy would just grow quadratically. No matter how far you go, energy keep growing. Yes, you would need to spend more and more energy to stretch, right? But things, when we say things are broken, because when we release them, they don't come back, right? So they're broken. They're just sitting apart. And this is this type of behavior where energy initially grows, but then there is a point after which energy, you're not paying more price energetically for extending the bond, right? It's broken essentially. Fragments don't feel each other, and that's why they don't attract each other, and they can be separated as far as you want without paying energy price, right? So that that point where the harmonic approximation stop working, you can kind of pay less and less price for stretching the same distance essentially. Right? And that's the reason, anharmonicity is essentially the reason why we can, well, things are broken. Now boing back to harmonic approximation, we discussed what the energies will be. By the way, compared to particle in the box energies, the distance grow, right? So because energies are proportional to n square, the delta energies are proportional to n. So the distance between the levels in the particle in the box, they're growing. While in the harmonic approximation, or in the harmonic well, energies are proportional to n, and the delta E is a constant. It's proportional to omega, right? So that's the interesting difference. Then the wave function. How do the wave functions look like? So the same kind of plot. And first is Gaussian. It looks like first particle in the box function. Only is that n is equal to 0 here, not equal to 1, like in the particle in the box. And but there is no region where wave function crosses the 0 line. First function, n equals 1, it contains q in front of the Gaussian, so it looks like this, symmetric plus and minus. This is only plus, right? And then you can see that the next term is quadratic, so it has two points where wave function crosses the 0 line, and so on and so forth. The higher you go, in order for the kinetic energy to grow, you need to have more and more nodes, and eventually somewhere where n is very high, and it looks more like this, right? With many nodes. Also, interestingly, that the functions that are presented here, if you think about them as a symmetric objects with respect to reflection, with respect to the the plane that is put in the minimum of the parabola, then they go even function. So even means that if you switch, say this is a negative and this is a positive part, and 0 is somewhere here, right, in the middle, right? So then this type of functions, if you put minus x, they will be exactly the same as having x here. So these are called even functions because this lobe is exactly the same as that lobe. But the next function is an odd function for which f of minus x equals to minus f of x. So I didn't plot it very well, but you can. I will upload a nicer picture or you can look at in Wikipedia or somewhere online. Essentially, this lobe will translate into the negative lobe exactly of the same size, but just going down. And then there will be even function, odd function, even function, odd function. The reason for that is, again, that the Hamiltonian of the harmonic oscillator actually commutes with the sign change, with the operation. If we introduce the operator, and it's usually called parity. So this parity operator, when it acts on the function, it changes its coordinate to minus that coordinate. Okay, and the reason why both particle in the box and harmonic oscillator have functions that alternate in even and odd behavior, you can check that, is because the Hamiltonians of both systems actually commute with parity operator. In other words, it doesn't really matter whether you whether you do this or you do this, the result will be the same for any function. Okay, and that's kind of easy to see because Hamiltonian of the harmonic oscillator, it only contains the essentially coordinates squared, so changing the sign in those coordinates doesn't really change the result of the action of the Hamiltonian. And so because these two operators commute, that means they share eigenfunctions, right? What are the eigenfunctions for the parity operator? Well, there are two types of eigenfunctions for the parity operator. They are either symmetric or antisymmetric. So essentially any function, when you act with the f of x, this thing can be either minus f of x or it can be plus of f of x. Okay? Oh, there are eigenfunctions. Sorry, there are eigenfunctions of p that have these two properties, right? So this would correspond to lambda, the eigenvalue equals -1, and this one corresponds to lambda equals 1. Okay, and then any random function, say g, if you take a random function, of course, when you change the sign inside of that function, it's not going to be a function itself with plus or minus sign. It's random, right? But you can always make a symmetric and antisymmetric combination of for any function. You can take this, and this will be a symmetric function or symmetric kind of combination. Then parity operator acts on the GSX will always be GSX back. And antisymmetric is G of x minus G minus GX. Okay, so this function, when you act on it with parity, then it always will be minus. You can check that. Okay, it's actually quite simple check because parity what does to the symmetric, it will turn this into this and this into this, right? And because they sum, then nothing changes. But here, if this guy will turn into this guy and this guy turns into this guy, the overall sign should change. Okay, so that's why it's easy to, if you have any function, it's easy to construct symmetric and antisymmetric version of the same function. And then the symmetric and antisymmetric, they will be eigenfunctions of parity. Now, what is this helpful for? Well, sometimes it's helpful if you know that the Hamiltonian of the system that you're considering, and you don't know how to solve the, say, eigenvalue problem for that Hamiltonian, you can use the variational approach. But if you know that the Hamiltonian is commuting with parity, that actually means that its eigenfunctions will be even or odd functions. And if you're interested in even function, there's no point to use, say, odd functions in linear combination that you are trying to use to approximate the function of your interest, right? So if there is a possibility, say you don't know how to solve the eigenvalue problem for harmonic oscillator, you know variational approach. So you put this potential in the box and you say, okay, I will approximate the harmonic oscillator ground state function as linear combination of particle in the box functions, right? Good. Well, one thing to remember though is the ground state function that you're interested in, it's even function. So there is no point of using n which is even for the particle in the box function. Why? They're asymmetric. That's right, because they are all that sort of that sort of type, right? So because the sine of 2px divided by L, sine of 4px divided by L, they all have a nodal line, and the function you're trying to approximate doesn't have a nodal line. So there's no point of using something that has a different symmetry to approximate a function of the different symmetry. Okay. Any questions? Okay then, let's consider then, what should we consider? Oh, I guess that's related to symmetry as well. Say if we're interested in spectroscopy, right, and as I was telling you, going between the states for harmonic oscillator, that's what happens when we do the IR spectroscopy, right? So we have a molecule, and then we say the molecule is in a ground state, and then the radiation comes and excites molecule into the first excited state, right? Now, maybe in general chemistry, in organic chemistry, they were telling you about this molecular dance, or maybe haven't told yet, but you know, different vibrations in the molecule, they have, well, if you have a molecule and many atoms, right, so there are different vibrations. Now, on the one hand, it looks nice when you see all these vibrations, but it's only classical representation of what actually is going on, because remember, if you are in eigenstate, nothing actually moves, right? So that's something to remember. When someone tells you, oh, molecule vibrates, well, it's only in a classical picture it vibrates. In a quantum picture, it just It's just a distribution of probabilities which are not moving in time. Okay? But when we introduce the radiation, then we change the state. And what becomes important is so-called selection rules. When we introduce radiation and it's in a ground state, potentially it can go from the ground state to the first excited state, or to the second, or to the 100th, right? Well, it turns out that if you analyze the intensities, there are simple rules that tell you that actually from the ground state, primarily things are going to the first excited state, but not to the second. And the reason for that is just the form of the wave function and the form of the, well, integral that characterizes what's the intensity of the transition. Now, I'm not going to derive this because it involves a little bit more advanced formalism. It's usually introduced in the C-level course that some of you may take later, right? But the idea is very simple. So as any property in quantum mechanics, intensity of the transition has certain operators, right, that characterize that process. And since it's a transition process, the intensity is given. It needs to account for what's the initial position, say in state n. We start at state n, and then the matrix element with the position operator x needs to be calculated. Then the absolute value of the square of that integral characterizes the intensity. Now, again, I'm not going to derive this, but state it more like as a fact. And it turns out, if you consider this integral, because now you know what the harmonic oscillator eigenstate functions are, right? If you calculate this integral, you can find that n can be only m plus minus 1. So if you have, again, this parabola, and you on an nth level, you can only go either up or down. One level down or one level up. And so that's the situation. And because when you go up or down one level, the energy change is in both cases omega, then you have a very simple spectrum. Omega, you have intensity that is proportional to this expression. Okay? Any questions? All right then. What else? Diatomics. Right now, so far we considered the situation somewhat simple one, where we have like support, one spring, one mass, right? In reality, when we consider, say, simple molecules, we have more than one atom. Say if we are dealing with diatomics, that's the situation where we have more than one atom. Then somehow we need to, well, transform Hamiltonian so that we can use all this formalism for, say, two atoms. So if we have, in classical picture, two atoms, one with mass 1, another mass 2, there is a spring, and again we are looking at this in one-dimensional case, right? The distance here is x2 minus x1, and then the classical mechanics, just Newton equations, they tell us that well, we can write x1, x2 equal to constant x2 minus x1 minus, say, RE, which is equilibrium. This RE is equilibrium position of our atoms, right? And then for the second coordinate, we can also write the Newton equation. Okay, we will do classical analysis because it's just much easier to work with the classical quantities. First, to see what variables can we define, and then we will essentially obtain the expressions that will be containing only one non-trivial coordinate. Okay, now these are Newton equations for two particles, but not all these particles are coordinates are important for the internal vibrations, because you can imagine if x1 and x2 at the same time move to the left or to the right, then there will be no contribution to energy, right? No? Not clear? You guys follow? So if you have two particles, what are you, texting or something? Are you asking friend? Or huh? Sorry? I see. Are you asking about this question or no? So you're not interested, or you can miss stuff, right? Okay. So if you have two particles and if they move together to the left or to the right, then there is no internal kind of energy change because the spring doesn't really contract or expand. So therefore, not all variable, not two variables are important here, but you may imagine that only the difference between the x1 and x2 will contribute to the internal energy. Now, in order to see that, we can simply sum these two equations, okay? And so what we do here is we take the masses, divide the right hand side, and then we subtract the x2 from x1. That's the kind of internal variable that we're interested in. Right, minus d okay, and then we can combine the two because the derivative is linear operation. and inverse masses x2 minus x1 e. Also, since this constant doesn't depend on time, we can put it inside and define new variable as x, right? The x2 minus x1 minus re, that whole thing is defined as x. And then from essentially this second derivative of the new variable is equal to minus k, right? This constant, okay, which I will call new variable mu, and this variable back x, right, that we have here. So we can write down the equation for this internal variable d2x dt squared as sorry, this is inverse of mu, right? So then it will be minus k mu minus 1 x and okay, so what we derived here is a Newton equation for the internal variable x that is the deviation from equilibrium position. And as you can see, we only need this internal variable. It doesn't, it's a second derivative acceleration essentially. It doesn't depend on any other variable, although we started with two, x1 and x2. Of course, from x1 and x2 you can form the difference that corresponds to the internal vibrations, and you can form the sum that corresponds to the translation of the whole molecule, in this case, right to the left. Right, because x1 plus x2, that's essentially the coordinate corresponding to change of both coordinates x1 and x2 at the same time. So that coordinate is not of interest to us because it doesn't really introduce any internal energy. Right, it's just the energy of the motion for the whole molecule to the translation. Okay, now the important part of this derivation is, although we started with two different variables and two different masses, the internal vibration of these two masses essentially correspond to the vibration of one variable with mass mu that is a function of masses of particles that are that were involved, right? So this is how we defined the mu, right? Right there, and okay. So then we have m1 plus m2 divided by m1 m2. And the mu then becomes m1 m2 divided by m1 plus m2. So the idea here is that if you have two particles and they are connected with a spring, the vibration or harmonic oscillator that corresponds to that system can be described by just one particle that is attached to some support, and all you need to do is to keep the spring constant the same, but mass should be accounting for masses of both particles, right? So that effective mass or we call it reduced mass, must be chosen based on this expression. Okay? And so then, if you do that, you are able to essentially reduce the problem with two centers to internal vibration of just a relative coordinate, but with a reduced mass instead of just well, the mass that we considered before was m. Now we have a different mass that is a function of two masses, which is natural because both masses you would expect to contribute to the vibration of the whole molecule, right? So essentially we reduce two-body problem to one-body problem, vibration, right? Any questions? All right then, I'll see you on Wednesday.